Welcome back to today's session. In the previous session, we have learnt about game theory. One more topic of this unit is dynamic programming. See, from this unit, you will get one very sure question, which is what is dynamic programming and what are the characteristics of dynamic programming, right? Anyhow, no problems from this unit will be asked in the exam. We will be learning this particular unit today, right? So what is this dynamic programming basically? We will have a look at it, who developed it, all these details, we will have a look into it, and what are the characteristics? How do you identify that a particular problem has to be solved using dynamic programming? All that we will be looking in today's session, right? So, talking about the introduction of dynamic programming, this particular technique, dynamic programming, was developed by Richard Bellman. You might have heard of Bellman-Ford's algorithm when you learned networks. You would have heard of Bellman-Ford algorithm. Even in ADA, you might have heard about it. So the same person, Richard Bellman, uh, developed the technique called dynamic programming in the early 1950s. See, this particular computational technique, which we are calling as dynamic programming, is also called as recursive optimization. Why do we call it recursive optimization? You will be understanding it in the future sessions, but for your information, let me tell you, in this particular method, we divide the problem into multiple stages, and each stage we try to optimize the solution, right? Recursively, we try to apply the same procedure for each stage and we try to optimize the solution. Therefore, this method is also called recursive optimization method. Actually, we don't have a standard mathematical formulation for dynamic programming problems, right? For each problem, depending on the variables given and the objective of the problem, one has to develop particular equation to fit for the situation. See, like in your linear programming simplex method, then your transportation problem, then in your traveling salesperson problem, assignment problem, you had a standard method of solving the problem. You don't have it, you don't have such a standard method here. So based on the type of problem, based on the objective function that we have defined, based on that, based on the situation or based on the case of the problem, we are supposed to define the mathematical formulation for the problem. Though we have quite a good number of dynamic programming problems, sometimes to take advantage of dynamic programming, we introduce multi-stage nature in the problem, right? As I told you earlier, to solve the problem more effectively or to optimize or to find the best possible solution, we divide the problem into multiple stages, right? We introduce multiple stages in the problem. We don't solve it in one go. We try to divide the problem into multiple stages and we try to solve the problem stage by stage and then optimize the overall problem. Fine. Nowadays, dynamic programming finds a lot of applications in your day-to-day activities. Many managerial problems are involved, such as inventory problems, waiting line problems, resource allocation problems, employee smoothing problems. All these are some of the examples of applications of dynamic programming, right? Shall we move on? So classification conditions for dynamic programming problem. How do you classify a particular problem is to be solved using dynamic programming? So that we will be understanding now. Dynamic programming problems may be classified depending on following three conditions. there are three important conditions based on which we will be classifying a problem as a dynamic programming problem. So the first amongst them is dynamic programming problems may be classified depending on the nature of the data available. So based on the data given to you in the problem, we will decide whether it is deterministic or stochastic. Stochastic is nothing but probabilistic models, right? In deterministic models, the outcome at any decision stage is unique. It can be determined or it is known. But in a probabilistic model, what happens is there are a set of possible outcomes, right? In your game theory, like you saw, when we decided the optimal strategy, you had multiple optimal strategies, but for every strategy, you had a probability associated with it. Similarly, here in probabilistic models, what happens is there is a set of possible outcomes. And with this possible outcomes, you have some probability distribution associated with it. Okay? This is the first condition. Second condition to classify DPP. The possible decision at any stage from which we are to choose one are called the states. So the decision that we choose in each of the stage is called a state of the problem, right? These states may be finite or infinite. States are the possible situations in which the system may be at any given stage. States are the possible partitions in the problem, and the situation or the decision situation in the stage is called a state. Anyway, we will be defining these terminologies in the next slide. The total number of stages in the process may be finite or infinite and may be known to us or sometimes even unknown, right? These are the conditions based on which we decide whether the problem can be classified as dynamic programming problem or not. So now we will have a look at few terminologies that we will be using in dynamic programming. The first term is called the stage. A stage signifies a portion of the total problem for which a decision can be taken, right? So this is a part of the problem for which an individual solution can be solved, right? You have an entire problem. So this problem is not dealt on a whole. So we consider a portion of the problem, and the portion of the problem is in such a way that you can consider or you can make decisions or you can find the solution for individual portion, right? So such a portion of the total problem is called a stage. At each stage, there are a number of alternatives, and the best out of those is called stage decision, which may be optimal for that stage, but contributes to obtain the optimal decision policy. See, for every stage, you can have multiple solutions available. A set of possible solutions are available. So out of that, the one best solution that you can pick is called the stage decision, which is optimal for that particular stage. For that particular portion, it is the best solution, but it may or may not be a part of the final decision, right? But it plays an important role in deciding the optimal solution for the entire problem. Fine? So this is about the term stage. Next we have one more term called state. The condition of the decision process at a stage is called its state, right? Stage is a portion of the problem. In the portion of the problem, you have a decision making process. A decision is involved. That decision process is called a state. The variables which specify the condition of the decision process, that is, which describes the status of the system at a particular stage, is called a state. Okay, the number of state variables should be as small as possible, because since larger the number of state variables, more complicated is the decision process. See, if you have less number of decision variables defining the state, then the decision process will be simple. See, if at all the more number of variables or more number of variables you have, the interaction between the possible interactions between the variables will be very high. Therefore, we may have to complicate the overall process, right? The process will be complicated. So to avoid the complication in the decision making process, we will try to retain the number of state variables as minimum as possible, right? So coming to the next term called policy. Policy is nothing but a rule which determines the decision at each stage. What will be the decision at each stage is defined or is clarified or described using a particular rule. Then that rule is called a policy. A policy is optimal one. If the decision made at each stage in a way that the result of the decision is optimal over all the stages and not only in the current stage, right? So we term it as a principle of optimality. Bellman's principle of optimality states that an optimal policy or a sequence of decisions has the property that whatever the initial state and the decision are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. So what does it actually mean? So let me say in the first stage, you used some principle, you used some policy, you used some rule to define the optimality for a solution. So your next stage optimality principle has to be based on the decision that you took in the first stage. Right, whatever policy you retained in the first stage, that should carry on throughout the problem. That is what your principle of optimality tells you, right? These are few important terminologies and concepts that we need to know with respect to dynamic programming. Then coming to the steps in solving dynamic programming problem. What are the steps involved in getting the solution for a dynamic programming problem? Or it can also be said it is the approach in which dynamic programming problem is solved. Okay, so first step is mathematical formulation of the problem and to write the recursive equation. Fine. What do you mean by recursive equation? Recursive relation connecting the optimal decision function for n stage problem with the optimal decision function of the n minus 1th stage subproblems. See, what does it actually mean? See, if at all I need to, let me consider an example of factorial and then correlate it to your optimal decision making recursively. So to find the factorial of 5, how do you find it out? You can write it as 5 into factorial of 4. In turn, this factorial of 4 can be written as 4 into factorial of 3. So for any nth value, the factorial is decided based on the n minus 1th values factorial, right? The same case here. But here we are not considering the factorial, but we are considering a decision. See, for the nth stage, if at all you need to define a decision policy, it has to be based on the decision policy of n minus 1th stage. This n minus 1th stage decision policy will be based on n minus 2th stage of the decision policy. This way, when you recursively define, it will be based on the first decision policy that you make. That is what your principle of optimality tells you, right? To write the relation giving the optimal decision function for one stage subproblem and solve it. So what we do is we try to define an optimal decision function which will find a solution for one stage subproblem, or let me say the first stage. We solve it. We find out the results from that particular stage. Using that optimal decision function, we will then go on. We will start building on it, and we will find the solution maybe to the next second stage, then to the third stage, then to the fourth stage, so on up to n minus 1th stage, and finally for the nth stage problem, right? That is what your third step tells you. To solve the optimal decision function for stage 2, stage 3, stage n minus 1, and then to stage n problems, we base it on the first stage decision policy. Now coming to the most important part of dynamic programming, which is characteristics of dynamic programming. So with respect to your exam, this is a very important concept, a very sure question, 100% sure question. Even before you get the question paper, you can start writing the answer. That much sure question it is. Characteristics of dynamic programming, right? So we will have a look at the characteristics of dynamic programming. Totally you have 7 characteristics. So we will look at it one by one. The first characteristic is problem can be subdivided into stages with a policy decision required at each stage. So the problem can be divided into n parts, and this division is based on the policy. Okay, a stage is a device to sequence the decisions, that is, to decompose a problem into subproblems such that an optimal solution to the problem can be obtained from the optimal solution to the subproblem. So what does it mean? The first characteristic says, if you have a problem in dynamic programming, we should be able to divide it into n parts, and there should be a policy to solve one part or the first part. So based on the first part solution, you should be able to define the second part solution, and based on the first and second part solutions, you should be able to define the third part solution, and based on first, second and third part solution, you should be able to decide the fourth part solution. This is what your first characteristic says. Coming to the second one, every stage contains a number of states associated with it. States are nothing but variables which gives the status or the current situation of the system, right? They are called the state variables. So every state contains a number of states associated with it. The states are the different possible conditions in which the system may find itself at that stage of the problem. Okay. Now coming to the third characteristic. Decision at each stage converts the current stage into state associated with the next stage. So whenever I am able to define a decision policy, when I arrive at a solution for stage 1, it should be it should be associated, it should associate itself, or it should influence, or it should lead to the solution for the next stage. That is what the third characteristics tells you. Coming to the fourth one now. The state of the system at a stage is described by a set of variables called state variables. Any given stage, the status of that particular stage is defined by the state variables. That's it. Now coming to the fifth characteristic. When the current state is known, an optimal policy for the remaining stages is independent of the policy of the previous ones. So if at all you know the current stage, let me say stage 3 status, you know the current state of stage 3. So you will be able to define an optimal policy for stage 4, stage 5, stage 6, so on up to stage n. You need not bother about stage 2, stage 1 and stage 0. That is what it says. It should be independent of the previous states. To identify the optimum policy for each state of the system, a recursive equation is formulated with n stages remaining. Given the optimal policy for each stage with n minus 1 stages left. So that is what I was telling you. To define an optimal strategy for n stages, you define it based on one stage along with the remaining n minus 1 stages. So for that remaining n minus 1 stages, how you will define? You will define it as one stage along with remaining n minus 2 stages. Right. This is the recursive relation that we need to maintain. That is what your characteristics number 6 tells you. Coming to the seventh characteristic, using recursive equation approach, each time the solution procedure moves backward stage by stage for obtaining the optimum policy of each stage for that particular stage. Still, it attains the optimal policy beginning at the initial stage. What does it actually mean? We are defining a recursive relation, right? So whenever we are supposed to find out the factorial, I am just giving you a comparison. Whenever you are supposed to find out the factorial, where do you start from? Do you start multiplication from 1? No. If at all they have asked you factorial 7, you will start defining from 7 into 6 factorial. Then you will take 6 factorial, you will write it as 6 into 5 factorial. Right? You are moving backwards. Starting from 7, you are moving backwards till 1. The same thing will be used in dynamic programming also. To find the solution of the nth stage, we are supposed to solve the problem. But directly nth stage cannot be solved. So you will define it recursively based on n minus 1 stage. So this n minus 1 stage is recursively defined based on n minus 2 stage. So we are moving backwards. Once you have found optimal solutions, let me say you know the value of 1 factorial, which is 1. So you will substitute it back. So you will substitute the value of 1 and multiply it with 2 so that you get 2 factorial value. Once you have got the 2 factorial value as 2, you will substitute it back in 3 factorial. You will write it as 3 into 2. so that you will get the value of 3 factorial as 6. So similarly, what we do is, in the backward process, we define the recursive policy, and whatever status you get from each stage, you will substitute it, and you get the optimal policy or the final solution in the initial stage itself, right? When we went and solved the nth stage, that is when you get the optimal policy. That is what your characteristics of dynamic programming tells you. Hope you people have understood. In the next session, I will be dealing with dynamic programming approach and one simple problem, which is called the employment smoothing problem. We will deal these two concepts in the next session. Thank you for your patient listening. Hope you have understood. If at all you have any doubts, you can post it on the classroom platform. Thank you. Have a nice day. Enjoy.